right, so this video, what we're looking at is equilibrium again. More specifically, how do we know which way the equilibrium goes? Which side does it favor? So again, remember equilibrium reactions, forward and reverse reactions are taking place at the same rate. So again, this has nothing to do with equal amounts. What it has to do is the rate of the forward reaction is the same as the reverse reaction. So I'm going to use this equation here, and I should write AQ down here for my product. So this is my reactant side, this is my product side, and again, that's always going to be the same way. And the reason I'm going to use this is called a complex ion. You don't need to know that. But the reason we use this as an example is because it has colored species. So we could actually see what is taking place in the equilibrium. So Fe3 plus is a yellow color, the SCN minus is clear, the FeSCN2 plus is a red color. So by looking at the test tube, because this is all taking place in the same test tube, if it's more yellow, that means the reactants are favored. If it's more red, the products are favored. So we're going to talk about how do we determine which way does the reaction go. So we're not going to spend too much time on this, but I'm just going to show you what we call an equilibrium graph to show you exactly what is taking place with concentration over time. So concentration is going to be in molarity, and we're going to be looking at this reaction over a period of time. So usually what you will see is you are starting with all reactants and you have zero product is usually how you start most equilibrium reactions. So let's say we have Fe3 plus and SCN minus, and we mix them together and we have absolutely no product. So product here, this is going to start at 0. The FeSCN 2 plus is going to start at 0. And let's say we have a concentration of Fe3 plus and we have a concentration of SCN minus. And again, we will talk about in other notes exactly how we get those values. But let's say we have a concentration of both of these. Well, what happens is the Fe3 plus and the SCN minus combine to make this. So that means these concentrations have to decrease. And then what happens is they eventually level off, and how much it decreases or levels off depends upon what concentration you're starting with and what equilibrium you have. And then this one is starting at 0 and then it levels off as well. Okay, now the point at which, and I may not draw this correctly, okay, the point at which we have all of them at a constant rate, we essentially have established equilibrium. So that means these concentrations of each one of these species is going to maintain unless I stress it. So that we talked about before with Le Chatelier is the fact that we could stress an equilibrium and move this. Well, the reason I brought up the color is Fe3 plus is a yellow color. This is a red color. So in the test tube, I probably end up with more of an orangey color because I have all of the two colored species in that equation. Okay. So again, this is a period of time that takes in order for you to find equilibrium. So how do we know which way the equilibrium goes? So what we're going to talk about is something called the Keq. Okay. Keq. Okay. EQ is usually a subscript. So it's a capital K. It is a constant at which a reaction will go. It tells us something about which way is it favored. So if my Keq is greater than 1, so this is going to be a math calculation, we will have products favored. If my Keq is less than 1, reactants are favored. And it's always going to be the ratio of the product concentration to the reactant concentration. Okay, so I'm going to show you what that means. So this is my reactant side, this is my product side, and again, because these are reversible, you must always have reactants on the left and products on the right. So for equilibrium, we do have to pay attention to what we call the coefficients. So what are the numbers in front of the chemical formula? So we're going to use the lowercase letters to be coefficients in a balanced chemical equation. And then capital letters are going to be the formulas of the reactants and the products. So Keq is always the ratio of the products to the reactants concentration. So what you see here is really the generic form of Keq. Okay, so this is the generic form of Keq that you see in all textbooks. So the brackets mean molarity. Okay, so what is the concentration of C brought to the power of the balanced chemical equation, D to the power of little d, and again, this is a multiplication between here, so some people might think it's addition, but you're actually multiplying the concentrations there. And then the reactants are over on the left, concentration of A brought to the power of A, concentration of B brought to the power of B. This is why, or if you remember back to your reaction rates, we do not look at stoichiometry when we are looking at is it zero, first or second order, but for equilibrium we do worry about the the balanced chemical equation. So back to my statement before, Keq is greater than 1. That means I have more C and D than I have A and B. So that means the numerator on top is bigger than the denominator, okay? And likewise, if the number is bigger on the bottom than on the top, you're going to see that it's less than 1, okay? So if I have a greater than 1, I told you the products are favored. That means I end up with more C and D in this equilibrium than I do A and B. If my Keq is less than 1, that means it stays more as A and B and doesn't really form much C or D, okay? So let's work a problem or two so you can kind of see how this plays out. So this is a very famous reaction that's called the Haber process. And let's see if it will focus a little bit more. So we have the Haber process. Nitrogen plus hydrogen gives me ammonia. So this is called the Haber process. So nitrogen plus 3 hydrogen will give me 2 ammonia. So the first thing you'll be asked to do is to find the Keq expression for this reaction. So all you're going to do is write the products in brackets. So write NH3, put them in brackets, and then bring them to the power that is in front of it. So there's a 2 in front of it, so I'm going to bring it to that power. There are no other products, so I'm going to then put in the reactant. So it doesn't matter which order you put them in. So nitrogen is to no power because there is just a 1 in front of that. We don't write 1s in chemistry. And then we have hydrogen. Put those in brackets, and they need to be in brackets, and bring it to the power of 3. So this is your Keq expression, okay? Products over reactants. So let's say we did the reaction and we produced so much ammonia, 0.1, and we started with so much hydrogen and nitrogen, but then we've gotten to this equilibrium. So again, that's why I kind of did the graph for you, is for you to understand that we are now at equilibrium here. So everything has a concentration. Everything has a concentration. So let's find the value of Keq. So all you're going to do is plug in these numbers to the Keq expression. Very simple, easy math. Okay, so Keq is equal to, what's the concentration of ammonia? 0.1 molar brought to the second power. What is the concentration of nitrogen? That is 0.25 molar, and I don't bring it to any power. And then what is my concentration of hydrogen? 0.15, oops, 0.15 brought to the power of 3, okay? So I'm going to do the math. So take 0.1 and square it and divide it by 0.25 and divide it by 0.15 cubed, okay? And check this on your calculators. You should get the number 12, okay? Now what's interesting is for Keq, there are no units. So very different from when we were doing reaction rates where we had to worry about what's the molarity over seconds or whatever it happened to be. In this case, Keq has no units. So you don't have to worry about canceling out the molarities or anything like that. So that's the second part of a Keq. First part is the expression, second part is to find the numbers. So this last question will always be, are the reactants or products favored? So what your question is Keq greater than 1 or is Keq less than 1? So 12 is greater than 1, so that means the products are favored. So therefore, it's going to be making more ammonia than it is going to have the nitrogen and the hydrogen. Okay, so the last one I'm going to do for you shows you some little caveat or little hiccup that you might find with Keqs. So this one, I want you to pay attention to the fact that we have different states of matter. Okay, the last problem we did, everything was a gas. Everything was a gas. So if I write my Keq expression, not understanding anything or looking at states of matter, I would write AlCl3 in brackets, and I'd write H2O cubed. Again, these would be multiplied. And then I have AlOH3, and then I have HCl brought to the third power. Okay, so with this, I need to understand that these are concentrations, all right? These are concentrations. Do I have concentrations of solids? Do I have concentrations of liquids? Okay, so solids and liquids don't have concentrations, okay? They don't have molarity, okay? They don't have molarity. What do they have? They have a density, okay, which is an intrinsic property of that substance. So because solids and liquids don't have molarities, you do not include anything that is a solid or a liquid into the KEQ, okay, always, okay? So that means I made a mistake here, okay? So the aluminum hydroxide does not belong in the KEQ, and the water does not belong. So really it should be AlCl3 on top and HCl cubed on the bottom. It's going to be your KEQ expression. But I do this in the notes just so you could see what mistake I made so that you don't make the same mistake. Now what I do, because this is more of a problem solving situation, I will give you concentrations of everything. So I'm going to not try to trick you, but I don't want you just to plug things in your calculator. So I'm going to cross out the aluminum hydroxide and the water concentration because I know I don't need them, okay? So I'm going to find my KEQ by putting my concentration of the aluminum chloride, which is 0.1 molar. So that goes on top. And what goes on the bottom is going to be the concentration of the hydrochloric acid, which is 0.2 molar, but I must remember the stoichiometry. There is a 3 in front of it, so I have to cube that bottom part, okay? So mathematically, it comes out to the number 10. Again, there are no units for KEQ. And then since this is greater than 1, I'm going to say products are favored. Okay, so again, that's the only little hiccup or thing that you're going to have to pay attention to with KEQ is you never include solids or liquids. So you do include aqueous, okay? You do include aqueous, and you do include gases, okay? Because aqueous and gases all have concentrations, okay? But solids and liquids do not.